Okay, so it should be recording to the cloud. I'm going to share my screen now. And we're going to start basically chapter 5. And here it is. All right. So one of the things that chapter 5 begins with is whether or not a function is increasing or decreasing. So as you look at a function increasing left or right, an increasing function, that basically means that whatever the f of x1 is, that is going to be less than some f of x2. Okay, so let's just draw a quick, easy picture to follow. So I'll just do a first quadrant where this is f of x1. And this is the x, obviously. So here's x1, x2. And in this picture, in essence, this is going in this direction. Whatever it is going up. So if I'm looking at this being f of x2, this value here, let's call it x1. This is the equivalent of x1 and f of x1. If you notice, if I compare it to this point here, and I'll call this point here 2 comma f of 2, that'll make it easier to listen to. That's basically what the premise is on the values in respect to the coordinate pairs. If it's decreasing, it's almost identical, just the reverse of it, right? So if a function is decreasing, that means that that value for f of x1 is going to be greater than some value of f of x2. Exact opposite. And that would look like this. So if I'm looking at just the first quadrant, this is x1, this is hypothetically x2. That means that f of x1 is somewhere up here, and it's going in this direction, so that some f of x2 is just less than that. And that's basically decreasing. I say it's simple as left to right. Is it going up or down? It's that simple. So you might want to consider focusing on, what's obvious, which is left to right, what's happening. Is it taking off? Is the plane taking off in a sense, or is it dropping? Okay. All right. The other third element that we looked at is constant, or is the line constant? And in that case, you're looking at f of x1 is equivalent to f of x2. Okay, and we're going to talk about this ad nauseum. This is also going to take us to why the critical points or the critical numbers are so important. Once you understand that the critical numbers help you define what the behavior is, we can then take off from there. So with that said, let me give you this example to take with you. For the sake of argument, let's call this f of x to be equivalent to x cubed. Got a little happy there with the cube. Let's call it x cubed plus 3x squared, nice easy expression, minus 9x plus 4. And what we want to do now is we want to find that first derivative. This is why we've been talking about derivatives this whole time. This gives us a new expression called 3x squared plus 6x minus 9. And if you consider the fact that I'm going to factor this is gonna, taking out the 3, which is common to all three terms, right? This is gonna leave me with x squared plus 2x minus 3. And I'm now going to factor this. And when I factor this, I end up with an x plus 3. And I end up with x minus 1 as a factor, which means that I have two critical numbers. What I mean by that is, when I solve for x, I'm solving for -3, so x equals -3, and here I get x equals +1. So I'm immediately thinking a number line, and I want you to think the same way. Where this is -infinity, this is +infinity, you have a -3 cutoff, in a sense, think of it as a cutoff, and a +1 cutoff. So that means that your values are sitting in intervals from -infinity to -3, union, not inclusive, -3, 1, again, not inclusive, union, again, 1, infinity, not inclusive. And what this tells me by using what we call a test point. So hypothetically, let's use, say, for example, here, the -4 point falls here. I'm going to use that as a test point. I'm looking here and I'm thinking -2. I'm going to use that as a test point. And over here, I'm going to randomly choose a value. Let's choose 2. And I'm going to use that as a test point. Now you can choose anything you want. I'm just using these 3 test points because that's what I chose to use. Now, this is where Desmos comes in handy. So notice that we focused on the critical points, and I'm focusing on -3, +1. So those points are important to me, and I'm going to show you why. And this goes back to maximum and minimum. So max and min, you're going to see on Desmos right now. So let's pull Desmos up. And we're going to go ahead and we're going to put in this equation. So I'm going to start with the x cubed. Notice that I'm graphing the f of x, by the way. Notice that I have x cubed. We're going to do plus the 3x squared and minus 9x and plus 4. And this is what our graph looks like right now. Okay, I'm going to shrink it a little bit. And that's what it looks like. That's the original f of x. And I want you to notice the value of this point and notice the value of this point down here. Let me see if I can grab that little tip. It's a little harder to grab because it's so tiny. Yeah, see how that's 1? And that's -3. And if you remember, those are the 2 critical points. Those 2 critical points are telling us there is something changing here left to right. Left to right, I can see that this equation is increasing from -infinity up to -3. It starts to decrease between -3 and 1. That I know it's going down. But yet from 1 to positive infinity, you can see it's going up. Is that clear to everyone how what's happening, or it makes sense? No, yes?
I'm sorry, can you repeat that again? What you just explained?
Sure. When you look at the original f of x, I'm asking you in terms of increase and decrease, do you notice that left to right from negative infinity up to this -3 point for the x, for the domain, the x domain, it's going up? Do you agree, left to right? Is it not going up?
Yeah.
Yes.
Okay. And then from -3 to +1, what's happening? Is going down, right? Left to right is going down from the two black dots, -3 on the domain and +1 on your domain. When you look at that graph right there, you can see it's decreasing. And then on the last half of the graph, from 1 to positive infinity, you can notice it's increasing. Yes?
Yes.
If you're unsure, you can always go back and say, okay, well, I used the test point here, and I'm looking at the value of f of -4. Sorry, that was my dog. F of -4, and you notice that answer is 15. So it is positive, so it's going up, and that interval. So this interval, we know it's going up. This is the interval where we noticed it's going down. So if you take a value like f of -2, you'll notice that that drops. Can you tell me what the value is for f of -2 for that one? Plug that into the equation. What are you getting? See if you beat me to it, because my calculator is. Oh, here, I'll actually do this on my online calculator. Excuse me. All right, let's go to my TI calculator so you guys can see it online and we could talk. All right, so I'm going to go to y equals, and in the y equals, I'm going to do my x cubed, my x raised to the third, x raised to the third, cranky calculator, plus the 3x squared. I keep forgetting that if I don't punch it in this way, it doesn't stick. I will not forget again, I promise. We're going plus 3x squared. Okay, so x, 3x, and we're going to raise that to the second power. The 3x squared. Okay, back out again. Minus 9x. Plus 4. All right, so I'm going to go ahead, now that I have this in here, and I'm going to go ahead and graph it so you can see it again. Let me shut this stat plot off because I have this on from a prior class. Okay, and I'll go to graph again. It should zoom. We're doing zoom standard. There it is. Okay, and so these are the points right here. This is that point -1, 1, or 1, -1 that we were looking at. So if I go to second graph, I said let's look at f of -2. F of -2 looks like it's going to be 26. The other number we looked at as I was playing with this was f of -4. So let's go to -4. F of -4 is positive as well, so that's going up. And so I said f of -2, we're at 26. There's possibly a mistake here. 3x squared minus nx plus 4. Oh, I'm sorry, I'm throwing this into the original function. So regardless, you can see in this case, if I'm looking at the graph, you can see left to right what's happening between the -3 on the x from here to here and the 1 it is decreasing. But then from the 1 for positive infinity is going to keep going up. And you can see that in the table as you look this way. You can see it's going up. So anyway, so with that said, if you go back and let's use the derivative instead. So let's use the derivative. I'm going to go with 3 parentheses negative 4 plus 3 as one example. Negative 4 plus 1. And I work that out. I end up with 3 times negative 1 times negative 3. And so that'll help me find my value. And then I repeat the process with negative 2. So we'll start with 3 times negative 2 plus 3 times negative 2 minus 1. And work with that as well. So anyways, this is how we're going to play with these numbers. And you can see that you end up with that first derivative. When you use a negative 4, you end up with 15. And in the second one, where we use the positive or the negative 2, you'll see that that also is leaning towards a lower value. So in this case, if I have, for example, f of negative 3, as an example, you find that the answer would be 31. So you play with those numbers, trying to determine what the behavior is of the graph. So regardless of the fact, your critical numbers, which are in this case, the turning points in your diagram, one of the turning points as you look at the diagram as a rough sketch was this one, which was negative 3 and 31. This was the max of this graph. So this being a critical number. The other critical number is in the min, where you end up with the number 1, negative 1. And this, you can also see this yet another turn. I also want you to notice another element just to refresh your memory. Notice this x to the third power. So that means that you have 2 turns, which you do here. This is how you know that you should have 2 critical numbers. Because remember, this is always n minus 1 in terms of terms. So this 3 minus 1, which is how we end up with the 2 turns. Trying to think what else I need to remember. Oh, we do know the intercept as well. Remember the basics here in terms of intercepts. You do have a y-intercept in this case, x equals 0. And so our intercept for the original function for f of x, our intercept is at 0, 4. So that's another way it can help you graph this equation. All right. I'm gonna do another similar concept, but just a different equation. I just want to open up the floor if you have a question that's sticking on your mind. Once, twice. Okay, so far so good then. All right, I'm gonna go to the next example. This actually is example 3 in your book. If you're following in this book, f of x is given to us as the equation of x minus 1 raised to the 2/3 power. So you need to remember in this case, you're going to use the chain rule. So we're going to begin with multiplying. So we'll multiply. So we have 2/3. And this becomes, initially it becomes x minus 1 to the negative 1/3. And obviously you times the derivative of the inside of this, which is 1, since it's 1 at x. We then correct it so that we get rid of the negative exponent. We'll multiply 1 times 2, so we end up with 2 over 3 parentheses x minus 1 to the positive 1/3. And now we can look at the denominator for the critical number. So if I look at this denominator, so this is for the critical number. Okay, so that means that we're going to take 3 parentheses x minus 1 raised to the 1/3, and we're going to set it to 0. So as we begin to solve, we divide by 0 on both sides, or by 3 on both sides. This cancels anyway, so you end up with x minus 1 to the 1/3 power is equal to 0. And then we're going to raise both sides of this to the 3 over 1, in theory. So technically this becomes x minus 1 is equal to 0, which means x is equal to positive 1. So this is our critical number. However, in this case, this does not exist, and I'm going to show you via picture why. And what ends up happening in this case, if I graph the original, let me go back to Desmos to show you. Close this out. Okay, so we're back to Desmos. So we have our original f of x is equal to parentheses. This is x minus 1, and this is raised to the parentheses 2/3. So you notice what's happening here. So anytime you have this type of sharp behavior, there is no derivative. The derivative doesn't exist at that point because it's not differentiable. If I choose a point out here, so I'm going to go back and draw this on a regular paper. Going back to this, okay, so just take a moment and just remember the quadrant is sitting here, such. Here's positive 1, which is important to us. And what I'm going to do, let me change the color of my marker. Let's use red. This is sort of jutting out as such, if that helps. And in that case, if I take the derivative, the first derivative, and I use a test point, let's use a test point of 0. So we can use this test point. So the first derivative is 0, and I'm going to use another test point. Since this is 1, I'm going to use 2. So again, these are randomly chosen. You can choose whatever you want. And we'll throw that into our derivative equation. So in this case, you end up with, so for example, you'll end up with 2 over 3 times 0 minus 1 to the 1/3, which results in 2 over negative 3. And so that is a value you want to take at heart. And same thing here is you're going to use the f of 2, so this will be 2 over 3 parentheses 2 minus 1, and this is raised to the 1/3, and this value also results in positive 2/3. So these are little points that we're using to gauge where this is happening. So in this case, we would say that we basically have a function that runs from negative infinity to 1. and it's at this point it seems to be decreasing, so this is a decreasing part of the formula. Because remember, we read this left to right, so in the second equation, or side of the graph, we're looking at this as 1 comma infinity, in which case this is increasing left to right. But the first derivative in this case, whatever that first derivative, is going to result in 0. So it does not exist. All right. Are you okay with that one? Is that one an easy one to remember?
Yeah.
Now, there is an example 4, which I'm going to share with you as well. And this example is pretty clear about the fact that it doesn't have critical points. So let me share with you this one. And I'm going to graph it on Desmos. Let's talk about it. So on this one, we can call it example 4 if you wish. It's saying f of x is equal to x minus 1 over x plus 1. And so if we use the quotient rule, obviously because we're dividing two functions, we're going to find the first derivative using the quotient rule. And this results in x plus 1 times the derivative of the second equation, which is just 1, minus x minus 1 times the derivative of that other function, x plus 1. And all of this is over x plus 1 squared. All right, and so we'll simplify this. As we simplify it, you're going to end up with x plus 1 minus x and then plus 1. Because remember that negative transfers in here, making that positive times a 1 as well. This is all over x plus 1 squared. And if we simplify this, this is 2 over x plus 1 squared. So once again, we're going to look at some test points. If I simplify this, you can see the critical number based on the derivative is -1. So if this were the y-axis at x is -1, we have a critical point. So that means that I have to use test points on either side of that. So I could potentially use, I could use -2. And once again, to make life easier, I could use 0. And so you could see, again, this being negative infinity to infinity over here on this side, that given that critical number -1, which by the way, let me show you why I say it's a critical number, and you'll see it in the graph itself. So let me get out of here. Let's go to Desmos. So we have parentheses x minus 1 divided by parentheses x plus 1. Do you see what's happening? And if I were to mark this with x equals -1, you can see why that is a critical point. Or there is no critical number in that case, because that just tells us that's where the graph changes direction. So we want to choose the test point that's alongside the left side and the right side of that. So let's look at the derivative equivalent. So if I use this model, okay, I'm looking at the first derivative at using the 2, -2 at that. based on the diagram, we saw that we have something over here and something's going on here. So f of -2, we end up with 2 over -2 plus 1 squared, which is equal to 2. Another value is the critical point f of 0. In this case, we have 2 over 0 plus 1, and we're squaring that. And that gives us also a 2. So we do have something to consider there. So we're talking about the limit, which if we use the limit function where we divide by x on both top and bottom, since we're looking at x reaching infinity, we're going to take the x minus 1 over the x plus 1, and we're dividing both of these by x. So if I were to change the color, you'll see it clearly. Where in this case, I'm dividing this by x, and I'm dividing this by x, I'm dividing this by x, and this by x. And what ends up happening is I end up with 1 minus 1 over x. This is 1 plus 1 over x. And you remember, in any denominator, if this denominator is becoming a huge number, the closer this number comes to 0. So that's another consideration for this. So in this case, that gives us a horizontal asymptote, right? Where x equals 1. So we have some horizontal asymptote going this way and another one going vertically. Okay. Same thing happens, by the way, if we look at it as x approaches negative infinity, we see that the graph has a line equal to positive 1, and that is the horizontal asymptote. And if we use the x-intercept to 1, 0, and the y-intercept was 0 or negative 1, we see the same occurrence. So you end up with a figure that looks like this. So just like you have that, we have a y equals 1, and so our figure kind of looks like that, if that helps. All right. I have 2 more examples, then we're going to take a quick break, if you don't mind. I'm going to finish these 2 up first. Okay. So in this next example, I'm going to call it example 5. We have been given an f of x, which is equal to 3x squared. And if you notice, in this case, it is basically a cubic, my bad. I wrote the derivative before I wrote, is actually just x cubed. I was just going to say, this is just a cubic function. If you look at it carefully, it's going through 0, 0, and it's going from negative infinity through the origin back up as such. And so we have what we call an inflection point. If you don't know the definition of an inflection point, basically the graph is going up on all levels. So left to right, it's still going up this way, and it's going to continue going up this way. So we refer to that as a critical number, yes. So the critical number for this is at x equals 0. But that just means that we have an inflection point. When we look at the domain for this, your domain in this case is still negative infinity to positive infinity. There's no change there. And if I take the first derivative of this function, so let's go ahead and let's do what I initially did, which is to give you the derivative, which is 3x squared. In this case, if I substitute in, for example, 1, I get 3 parentheses 1 squared. Well, that's in this case going to be 3. And if I were to do -1 as a test point, so 3 times -1 squared, I still get 3. So we have basically to look at the left and right side. So here's your -1, there's your +1. And so we are looking at that first derivative value. And so what we have in this case is a perfect example of one where you simply have an inflection point. Okay. Okay. Why don't we take a little break? Let's make it a 5-minute break. Is that cool with you? And I want to go into the next section, which is talking about in this case local extrema. And I want to talk to you about local extrema relative maximum minimum. And then I want to talk about profit analysis, and then our day is over. So let's take 5 minutes if you would. I think you can use the quick break because I know I go on and on and on and I don't stop. So 5 minutes. Let's reconvene at 6:45. Is that cool?
Yep.
All right. I'll talk to you in 5 minutes. All right, so coming back, I'm going to talk to you real quickly about relative extrema. And they, just for the record, they also refer to this as local. So you might hear this as local min or max, or, relative extrema, that they're really just talking about what is the value, what's happening at this particular point. And in the diagram and these, whatever you're measuring. And so the first example I want to toss at you is something that you could probably relate to. So I'll call this example 1 in the second part of the lecture, where I'm talking about something as simple as you're maximizing a viewer's attention. So this is like a work related question. And it's as simple as this. It's a local max and min. So if they're telling you that there is a function that actually models the behavior of a person, that's a viewer, you would look at something like f of t, and that is equal to negative 3/20 t squared plus 6t, and then plus 20, which this is actually time. And they're looking at the viewing attention, or as less 0 minutes less than or equal to the t, but less than or equal to 30 minutes. And so they want to know when is the best time to have an advertisement. So if you're maximizing the viewer's attention, you're trying to catch them when they're most I guess attentive. And so of course the first derivative is what we want to look at, because that's the change or rate of change. So here as that first derivative, which after we do a little math, this becomes negative 3/10t plus 6. And a little math simplification here is that is the equivalent of basically of negative 0.3t, that's just math, plus 6. And so if we're looking for this to be true, let's see if we solve for t, what happens. You would end up with negative 0.3t, in this case, plus 6 is greater than 0. If I subtract the 6 on both sides, I have negative 0.3t is greater than negative 6. And therefore, according to this, at about t, approximately 20 minutes, that's where the viewer is likely to be paying attention. So I'm not going to graph this one with Desmos, but I am going to at least give you a hypothetical here. So if you look at the graph from here to here, they're looking at the maximum point, where if I substitute in 20, this becomes 80. So in this case, the maximum level of the attention is about 80%. We relate to this as the relative max viewing attention. Another way to think of this also is as relative extrema. So in this case, if they want you to find, this would be a typical question, find the relative extrema, and they're giving you f of x is equal to 2x cubed minus 3x squared minus 72x plus 15. And so we find that first derivative. Once again, this is going to leave us with 6x squared minus 6x minus 72 equal to 0, which we can now factor. I know 6 goes into all three of these terms. So if I take out 6, I end up with x squared minus x minus 12, and all of this is equal to 0. I now need to factor this. Can I think of two numbers that'll give me 12 as a product, but be 1 unit apart? And so I'm immediately thinking this has to be x minus 4 times x plus 3, and that's equal to 0. Which means that I have x equal to 4, and I have x equal to -3, which are my critical numbers. Okay, and so what I want to do is now, using these critical numbers, we're going to take that first derivative value. So if I take the first critical number, assuming we use the number line method, so here's negative infinity, infinity, here's -3, and over here is +4. I have an interval from negative infinity to -3, union, -3 to 4, union, 4 to positive infinity. So I want to test some points. Let's use some test points. I'll do them in red to differentiate them. And so let's use -4 over here. That makes sense. So this is my test point in red. I'm going to use 0 because 0 is super easy as a test point here between 3 and 4. And over here in 5, I'm going to use another test point. And so we're going to see what happens. So at first, if I look at first derivative at -4, and I plug this in, this is 6 times -8, because -4 minus 4 times -4 plus 3 results in a value that is greater than 0. If I do the first derivative and I try the 0, I end up with 6 times 0 minus 4 times 0 plus 3, and that gives me a value that is less than 0. And again, that first derivative given 5, I'll do 6 times 5 minus 4 times 5 plus 3, and that's going to give me a value greater than 0. So as I'm thinking of the critical numbers, I'm thinking I have a positive association here, a negative association here, and a positive association here. So when I look at my figure and I graph it, I'm going to get something that should look something like this. Okay, and so what you want to do then is, let's go ahead and let's graph this on Desmos. So graphing the f of x, and I'm going to put 2x cubed minus my 3x squared minus 72x, and lastly plus 15. And I gotta open this up a little bit, so I'm gonna try and do a window from 5 to 5. I'll narrow this down a little bit. Bear with. This looks huge. Make sure I have the right numbers. Yeah. Oh, it's a 72 that's killing us on the graph. You can kind of see what's happening here. Let me see if I open it up. It's impossible to see it. Let me just graph it for you this way. I kind of already did, but this is kind of what it looks like. It's going to. What does go? Let me see if I can swap. Okay, so one more time. It looks like at -3, 150. So let's pretend this is 150. So -3, 1, 2, 3. So we're up here. This is the point -3, comma 150. And then it kind of goes through 0, 0, and it drops back down to all the way down somewhere to like -193, where x is 1, 2, 3, 4. So somewhere around there, it's hitting here. And so this diagram kind of like does this behavior, where it kind of loops and comes back. And so this point is 4, comma -193. You can substitute it in. Obviously, these are our critical points, which I talked about. But yeah, you can still see the behavior where it's going up and then it's going down. And then between the two numbers, of course, which is what I mentioned initially when I did the plus minus. So that's an example of relative extrema. And it helps you determine, like, prime shopping cycles, or when viewers are paying attention to something, or something along those lines. Let me do one more example of relative extrema, and then I want to do like a semi-word problem. So here's example 4 in this particular example. So we're still on relative extrema. I hope you can see that this section is fairly easy. We're taking the function in this case, which is f of x is 6x raised to the 2/3 minus 4x. We'll take our first derivative of that, which in this case is going to give me simplified to 4x to the -1/3 minus 4. And so you can re-express this as 4 minus 4 over x to the positive 1/3 minus 4. So that would be your first derivative. If I set this to 0, so we could start talking at the first derivative set to 0, so 4 over x to the 1/3 minus 4 equal to 0. We would first add the 4 to both sides, so you get 4 over x to the 1/3 is equal to 4. And if we swap these out, or multiply this by x to the 1/3 on both sides, this will cancel it on this side, leaving you, in this case, 4 equals 4x to the 1/3. If I divide by 4 on both sides, this now becomes where 1 is equal to x to the 1/3. Now, if you do recall, I am gonna get rid of that third 1/3, so I'm gonna raise all this to the 3/1. I'm gonna raise this to the 3/1. So x is equal to 1. Obviously, x is equal to 0 is the other critical number that I mentioned up here. So you do want to take an advantage of the fact that f of x equals 0, if that is true. So it has to be 0 because of the denominator that is sitting here. That can never be 0, right? So as I'm looking at this particular number line, from negative infinity to infinity, I have x is 0 and x is 1. I'm selecting my critical points at this point. So I'm looking at, let me shrink this back, go back to this. And I'm gonna select my points. Let's select -1 as a critical point. Between 0 and 1, I dislike using fractions, but let's use 1/2 because it's fairly easy. And the third critical point, and let's go with 2. So these reds are my test points. My two critical points, 0 and 1. And now we plug them in to see what happens in the graph. If I graph the original graph, let me go ahead and do that just for your visual. You're going to see that this has a couple of points that are questionable. So we have f of x, where this is equal to 6x, and this is raised to the 2/3. Close that parentheses. And this is minus 4x. So let me go over here. Take a look at what this graph looks like. Let me go back. I think I had to go down this way. So yeah, see how dramatic it is? See that 0 point where it's almost looks like a checkered. And so that's not even differentiable at that point. Okay, so that looking at that graph, you can see that there's an extreme there. And so given that, we can go back to our equation. We know that there's a value of 1 where we plug in 1, we're going to get 1, 2, and that's going to be a maximum for us. So our intervals, let's talk about the intervals. We have from negative infinity to 0, which you saw the behavior, union 0 to 1, and you saw that behavior, and union, and this goes from 1 to infinity. And so once again, we could see the function is increasing between 0 and 1 because it does this checkered behavior, right? And so we know it's positive in this intersection, negative on the other ones. Left to right is going down. So at f of 1, we saw that it was equal to 2, and we know that this is the relative maximum. It's the relative max at that point. So you just have to take a moment with all of your different equations and see what pans out. So I want to talk to you about an example about bike sales, and then another example about relative extrema that has a little bit more of an inflection point. So I'm going to start with that one real quick. So the question that they're asking us here is to find all relative extrema. And they're giving us the function f of x, and that's equal to x to the third power e to the x. Remember, the derivative of e to the x is e to the x, so it doesn't change. So we're going to treat this like power rule, right? Because this is product rule, not power rule, product rule. We find that first derivative using product rule. And so that's going to give us x to the third times e to the x plus e to the x, because that never changes, times, again, the derivative 3x squared. So notice that these guys are your u sub x. So this is your u sub x, this is your v sub x. So u sub x, first derivative of v of x multiplied, plus the v of x times the derivative of u of x. Okay, so that's, if you need to rehearse that, that's good. That's also good. Okay, now remember, we're using this to get the critical numbers. And so this gives us, for example, e of x is equal to 0, or x squared is equal to 0. Or another way we could look at it is if this is x plus 3, because if I take out e of x squared, I can take out x plus 3, and so therefore this equal to 0 means that another factor is the x plus 3 equal to 0. So therefore another 0 for us is -3. So we do have to pay attention to those, the 0 and the -3. So once again, here's negative infinity, here's -3, here's 0, here's infinity. What's happening at that point? So it's as simple as, let's use that first derivative function at 0, or use the first derivative function at, say, for example, -4. We could use it at -3 as well. And let's just play with the numbers. So if I do f prime, the first derivative for -4, I'll notice using that test point that my answer will end up being negative. So that's if I use -4 as a test point. Another test point would be if I use -1, which would sit in here. This one actually ends up in a positive. So if I do that first derivative at -1, you end up with greater than 0. Here's less than 0. Let's do another test point here. Let's call this test point 1. So another test point, this one is also positive actually. So you end up with f first derivative at 1. And you can just throw that in the calculator and you find that this actually will be greater than 0. It'll be a positive number. And so that's giving us an idea that this diagram, whatever it is going, and so in this direction in a sense. It's eventually going to hit and jump. So let's look at a Desmos once again. If we graph it, we could see it. And so here's Desmos. And we're just going to do x raised to the third. And then this will be e to the x. So that's what our function looks like. I know it's kind of weird. That's why I was like, okay, that's what it looks like. You can kind of get the behaviors as you can see it, but you could see the behavior at 3. So that's one of the values that we talked about, -4. If I hold it at -4, it's about there. There you go. Oh, there you go. So that's a -4. That's why I said that's going to be a negative. A -1, you notice a -1 is starting to go positive. So it's starting to go up. And if I look at +1, well, obviously +1, you can see definitely it's going up. There you go, up a little more. Maybe here. Yeah, right there. You can see it's definitely going up. So don't be afraid to use decimals to help you make a decision on what's happening in the graph itself. Okay, I want to talk about bike sales, and then after this, we'll call it a night, so we're almost done. So this example is all about bicycle sales. So again, a business model. And it says there is a small company manufacturing bicycles. They give us our demand function, D of Q, where that it has to be greater than or equal to 0. So this is what we call a non-negative function. It's a 0 function. And they are telling us that the cost of Q bicycles is modeled as 10 plus 5Q plus 1/60, sorry, Q to the 3rd power. It looks like the price per bike, or the p-value, is the demand of Q, which is equal to 90 minus Q. And so when they give us this question, what they're asking us is to find the maximum weekly revenue. And so remember that when we talk about revenue, the R of Q minus is equivalent to the Q times the price, number of bicycles times the price. And that, according to their model, is Q times 90 minus Q. And that is equal to 90Q, terrible letter for use, minus Q squared. So you're basically turning it into a quadratic. And we want to maximize I misspelled. I want to maximize R of Q. So in this case, to maximize it, what we want to do is to find that first derivative. And so we're going to take that first derivative, set it equal to 90 minus 2Q, and set that equal to 0. And so we solve, we end up with 90 is equal to 2Q, and therefore Q is 45. So this 45 is our critical number. So if that's the case, then let's use a value on both sides of that. Let's look at that first derivative at a value of 40 and see what we get. And let's look at that first derivative at a value of 50 which obviously 45 is right smack in the middle. And you could see that in this case, we're at for this value, we have 10. Sorry, I had to do the math. Now for this value, we have negative 10. We can see that there's some increase happening at R of 45. So let's find that number out. So you throw that into your calculator, and with Q at 45, you end up with 2025, which is the maximum net revenue. That is your max revenue. And in that case, that will happen if 45 bicycles are produced. That's why 45. And we want to find that weekly profit. So let's call this example B, where we're focusing on the profit of creating or selling those 45 bicycles. We end up with a function in this case where they give us the profit of Q, which is equal to the revenue of Q minus the cost of producing Q. You end up with, in this case, something equal to 90Q minus Q squared, which we talked about earlier, minus the cost of the Q, which is the initial function of 10 plus 5Q minus 1 over 60 Q cubed. Now remember, this is given to you. You don't have to come up with these. So go ahead and distribute the negative. If we distribute a negative and collect like terms, you end up with negative 1 over 60.
Shouldn't it be 1 over plus 1 over 60?
No, negative. Remember the negative out here.
Oh.
And this actually initially is positive. That's why it becomes negative. I was thinking ahead of time. So you are correct, had that not been incorrect. So yeah, so distribute the negative, collect your terms, you end up with negative 1 over 60 Q to the third. You're going to end up with negative Q squared. Just collecting the like terms, you're going to end up with negative, well, actually positive 85Q. And then lastly, minus 10. Okay, so now what we're going to do is we're going to find this derivative, because remember, this is just the P of X, or the P of Q in this case. So we find that first derivative, P of Q. Remember, you're multiplying by the exponent, so 3 times negative 1/6, you can end up with negative 1/20th. Q to the second power, because you take it away 1, minus 2Q plus 85, and that equals 0. All right. And now what we want to do is, as we look at this, we could use the quadratic formula to solve for Q. We can also graph it. You will end up in this case with a Q value, and you can use, like I said, you could graph it if it's easier for you, or you can just, I think graphing it probably would be the easiest way. Because I know that's what I used when I was doing the example to share with you, is in this case you get something approximately, so it's not exactly, approximately 25.8, and the other Q is approximately negative 65.8. So remember, in this case, to graph, either graph or use the quadratic of some sort, or some technology that'll help you find it. And so what you find here is you can't have a negative Q. That doesn't make sense for us. So either the bicycle exists or it doesn't exist. So the company is not going to sell you negative bicycles, if you think about it. So your only critical number is the positive. So now what we want to do is we want to substitute in that value. So is this going to be a max value or a min value? Now it's as simple as use negative b over 2a. If you remember basic math, that is your axis of symmetry x value. And then plug this back into the equation and you'll get your answer, which is why we want to plug in that 25. So if you plug in that first derivative, or for that matter, just plug in that first equation, take the 25, plug it in, you get 1229.58. So that is a profit. You also could look at the value of P of 26. And again, I used a calculator at this point, and I got 1231.07. So it went a little bit up. So it looks like this is the max. If you want to see this, let me see if I could throw this, if you have the patience. I know it's getting late and you guys are tired. Let me see if I can throw this function like I did earlier in my calculator for my own knowledge. So I'm going to jump in here. I'm going to go with parentheses. And I'm going to put in negative 1 over 60. It may be a problem for me because I don't know this calculator will be happy, shall we say. But let's try. It's going to do x cubed, so don't worry about the variable difference. It's not going to care. Minus q squared, so minus x squared. Let's see if I can show you what I'm trying to show you. Plus 85x and then minus 10. Fingers crossed that this shows. Let's see. Oh yeah, thanks. Appreciate that. Go back. Let's put in a little integer instead. A very sensitive calculator. Just a little integer. We try and graph that again. Yeah, there you go. Okay, so you obviously cannot see it right now because the window is huge. However, I'm going to go to second graph and let's just look at the table. And you can see why I'm saying 25, 26. So here's 25, here's 26. What do you notice here? Just look at these three numbers. What do you notice? You see how this is right in the middle? And it looks like this is probably the highest I'm going to go. That's 1229, and this is 1228. That's 1231. Are you able to see that?
Yeah.
Okay.
Yeah.
So that's why this is our magic number. You need some sort of way to graph these numbers because the numbers get a little crazy. And decimals, I don't think will do that for you. That's why I suggested that Wabbit Emu or some sort of graphing calculator where you could do this. You can also do this on Excel. Dare I say that? Can I show you that trick? Would you
Yeah.
like you want to see that trick? Let me show you that trick. So in Excel, all you need to do is train Excel so that X is like a cell. Okay, so let me go here. So for example, I know that the numbers, since we already know it, I'm going to keep it simple. Normally I would tell you write down like, 1 to 40. I'm not going to ask you to do that. But let's do like 20, 21. 22, 23, 24, 25, 26. That was our magic number. 27, 28, 29, and 30. So what you're going to do is you're going to write down this expression. You're going to literally go parentheses and -1/60. And then close parentheses, and this is times x raised to the third, as an example. So whatever this is, you're going to raise it. So that's what, A8. So I'm going to go back here. This is equal to, and I'm just going to call this a to the third, or A3, right, as a function. Actually, I used A8. So let me go A8. This is a 26. Okay, so going back. So this is A8. Okay, and then the next number was minus, and then we have the same A8 raised to the second power. And I actually forgot to raise this to the third power. All right, and then we have minus 2q, so minus 2, I guess it's times, not q, but just the A8, because that's what I'm focusing on. Am I going to 85q? I'm sorry, not 2q. Minus, this is plus 85q. So I need to fix that. Go back and I go plus 85q, which is the equivalent of our 10, and then minus 10. Now, assuming I put this in correct, which I hope I did, these are the variables. The A8s are like the x's in a sense. So you can actually do the whole spectrum of numbers. I just happen to have chosen A8. So let me go ahead and hit enter. And I will notice where the answer is. It's actually right at the tip. Look at your answer. You notice it's exactly what we got on the calculator. And so the reason why I say that is because if I'm using like I'm using A8, what if I use this one instead? I'm going to choose A2, so I want this to be A2. It should be following me. Like if this is A2 instead, and I change this to A2 instead, and same thing for here. See, it'll give me my values as I go down. So if I do, let's see. So yeah, what it's doing is because I messed up and I started too early up here. If I do it side by side, which I could technically still do that. You guys can do this on Excel, and it's really cool. So let's do A1, and I'll change this all to A1. As long as your formula is the same, you should be getting the same answer as your calculator. So if I do that and I drag, it should. Yeah, see? At 26, A8, notice that that's my value. So that is an option for you. It is a cheaper, easy way to get those big numbers settled. So, all right. So the idea here is you're looking at that maximum minimum or relative maximum minimum to find your maximin for your function. Just remember that those derivatives will not exist when you have jagged edges or you have values that are extreme, like they're not smooth curves. That's where you've run into a snag, so to speak, relative to using the derivative. So Anyway, so remember, once again, let me go ahead and stop the recording here so you don't have to listen to me blabber on.